Hello everyone. I'd like to go over the exercise that we did in class so you have it as a reference. So if I go to this link here, 8 puzzle breadth first search exercise, we can see what this is all about. So it's actually best illustrated by this little app that Merhaf Susli made. And so let me show you what the puzzle is again. So if I say show these numbers, this cute picture of a dog gets shuffled up, and the goal is to rearrange these pieces in the grid so that they go in ascending order and that the only gap is in the lower right. And I can only move a piece into a gap, right? So I could move the 8 there, I can move the 7, I can move the 5, 6, 1. But I'm not so good at this. So I'm going to use the computer to help me. And what I'm going to do is try to represent this board as a two-dimensional array, and then think of adjacent boards as nodes in a graph connected by an edge. So let me show you what I mean. Okay, so here's the board we were just looking at, and there's 3 possible moves I could make from this configuration. One of them is that I could move 4 to the left. So let me make a copy of this and keep everything the same, except I'm going to move 4 to the left. All right, so then the board would look like that. Another thing I could do is move this 5 down. So maybe I'll depict that like this. So I'll replace the 5 with just this space, and then I'll move the 5 down here. Okay, so there we go. And then the other thing I can do is move the 1 up. So let me depict that like this. So I will put the 1 in this spot and swap it with a blank right there. Okay, and so what you can do is think of each configuration of the board as a node in a graph. And I'll connect these configurations with an edge if they can be reached with a single swap of the blank and one of the tiles that's there. And so now I could think of this as a graph where I'm trying to find a path from where I currently am to eventually, who knows how I'll get there. You know, this also has neighbors. Maybe it comes out of that one, I don't know. But eventually I want to end up at this configuration where I have 1, 2, 3, 4, 5, 6, 7, 8, blank. Okay. And so maybe just for clarity, maybe I'll add one more neighbor here. So this one is actually going to have 4 neighbors because there's 4 different things that I can do to get to another configuration. So let's say that I were to move the 3 up, for example, and so then that would lead to a board that looks like this. Okay, so that there we have this neighbor. So right off the bat, probably I would say the most interesting thing about this is the fact that we can think of it as a graph in the first place. Maybe not obvious that you look at the 8 puzzle problem and think, oh yeah, that's a graph. So oftentimes that leap of faith is the biggest insight that you can have. And now the rest is we're just going to grind through breadth first search. Because breadth first search will explore the whole graph, and it'll eventually get us to the goal. And when it does, it will get us there with the shortest number of moves, it turns out. But actually, we're just interested in solving the puzzle, so just getting to the goal is already interesting. Okay, so let's now jump back to the starter code for this exercise. And what you'll see is that I've encapsulated a configuration of the board with a class called state. And the state wraps around this two-dimensional array called tiles, which holds a configuration of the board. And then I have a little method here called, it's the repr method as part of the Python data model. This is going to return a string that represents the board, so when I print it out, it looks all nice. So maybe let me start by initializing the board with the state that I have right now, so that hopefully I'll eventually be able to solve what I'm seeing up here. Okay? So let's do that. I've got 5, 6, 8, blank 4, 7, 1, 3, 2. So let's do it. So I'll say state equals state, so make a new object of this. and it's supposed to take in the two-dimensional array that represents it. So it would be 5, 6, 8, and then blank, which is represented by a string of just space, blank for 7, and then 1, 3, 2. Let me check. 5, 6, 8, blank for 7, 1, 3, 2. 1, 4, 7. Yeah, okay, good. All right, so let's go ahead and just print that out and make sure that that repr thing is working. So let me pop in a terminal here. Give me a second, I'll switch into the right. Okay, now when I type python apuzzle.py, prints out that state. Great. So in order to do breadth first search and explore this, the first thing we need to do is add the functionality to actually build the graph on the fly. So starting at this vertex, we want to be able to get its neighbors automatically and then add them to the frontier. So I created a little skeleton method here called getNaibes, in which I'm going to do just that. I'm going to make a list of state objects that represent the configurations that I can get to by swapping a blank with something that's there. So the first thing I need you to do is figure out where the blank is. All right, so find the row and column of the blank. So what I'll say maybe is first row is equal to 0, column equals 0, and then what I'll do is I'll just loop through the whole thing. So I'll say for I in range n, for j in range n. So actually n is the resolution of this. It's 3 in the example I have, but I made it general enough so that we could support bigger puzzles like 4x4. You would say 15 puzzle, for example. So I'm just going to loop through the whole grid. I'm assuming it's square. And so I'll say, okay, as soon as I find, so self.tiles. If self.tiles index ij is equal to that blank space, then I've found it. So I'll say row is equal to I, col equals j. All right? So let's just test this first. So before I do anything else, I'm just going to call this method on the example that I have here. So I'll say print, or I'll just say state.getNaibes. And this will print out the location of the blank. So it's telling me it's at row 1, column 0. Looks right for that example. I should probably test it a little more thoroughly, but in the interest of time, I'm just going to keep going for now. Okay. So once I've found that element, what I need to do is, so let's say step 2, swap this index with every neighbor that it can be validly swapped with. So what I'll do is I say, okay, for ij in, so I got to consider the possible neighbors of this. So it would be, okay, the one above this, that would be row -1 column, right? So in this case, that would be like swapping the blank here with the 5. That's a possibility. I can also do row +1 column. That would be the one below. Oops, let me make sure I get this right. So I'm going to unpack this list of 2-element lists here. I can also go to the left, which here is out of bounds, so we'll have to deal with that. But so I'll say row, same row, but column -1. And then I can also go to the right. So I would say row, col +1. All right, so those are all the possibilities. And what I'll do is I'll just make sure that they're in bounds, okay? So like I said, here, I can't actually pull from anything to the left because it's at the boundary here. So it could have up to 4 neighbors, but it may not have that many. This one only has 3. Okay, so let me just make sure that I is greater than or equal to 0, j is greater than or equal to 0, I is less than n, and j is less than n. All right, so we got that. And if that's true, okay, this is a valid swap that I can do. And what I should do, I need to be a little bit careful here. I need to make a copy of the board, or I need to make a new element. I need to make a new state. So I need to make sure that I make a completely new state that's separate from this, and if I do any modifications to this, they don't affect that new state. So I did implement a method here called copy, which creates just a copy of the board and makes a new state out of it. So let me call that method. So I'll say, n for neighbor is equal to self.copy. Right? So that's going to make a new state object which has a deep copy of the entire 2-dimensional array here. And so any modifications that I do to this are completely independent. I wouldn't want to accidentally change this current state in self as well. I only want to change n. So what I'm going to do here is swap row column with ij. Okay? So I'm going to swap this blank with the open, or with the neighbor that I'm going to pull into to the blank. Okay. So I would say there's a nice little tuple assignment that you can do in Python to swap things. So I would say n.tiles row call equals n.tiles ij. And then I would also have to say then tiles ij gets what's at row call. So this is a nice little swap thing you can do in Python. And then once I'm done that, I will start to accumulate these neighbors into the array here. So I'll say nabes.append n. Okay, so let's test this real quick. So what I'll do is I'll say, okay, print out the state here, and then I'll say for n in state.get nabes. Let's print n. And I'll print a couple line breaks there. All right, so let's try to run this, see if I got it right. Okay, so supposedly it has 3 neighbors. Let's see if they're the valid ones. Okay, here we go. That's moving the 5 down. That's moving the 1 up. And then that's moving the 4 to the left. Okay, good. So it looks like I got that. Now, the last thing I should do is I need to know when I'm done, when I've actually found the goal state, as I described it here. So how do I know when I've reached this point? So I have also another skeleton method here, which is for finding the goal, and it's called isGoal. So somehow I want to say, okay, I'm going to go through and return true if this state actually is the goal, or false otherwise. So let me loop through here. I'll say, okay, for I in range n, for j in range n. So I'm going to loop through the entire board row by row and make sure that we actually are going in ascending order here. And so I guess what I'll do is I'll have like a little counter. I'll start it at 1, and I'll say, okay, look, every time you loop through an element here, you should increment this counter, right? So it should go 1, 2, 3, 4, 5, 6. And I'll make sure that, I'll say, you know, if self.tiles at index ij is not equal to the counter, then the result is false. But actually, I only need to do this until the very last tile. So I will also just make sure that I'll just say that if I is less than n minus 1. No, I guess I'll say if if I is equal to n minus 1 and j is equal to n minus 1, then it should be the blank. So by the time we've gotten there, we're okay. So really, I want the else of this. I'm doing something my students do all the time, which is writing an if that doesn't do anything, and then writing an else. What I should do instead is use De Morgan's law and invert this. So I should say, if not this condition. So that would be if I is not equal to n minus 1 or j is not equal to n minus 1, then I would do this. Okay. So as long as I'm not at the end, if I is not equal to n minus 1 or j is not equal to n minus 1, that's where the blank's supposed to be. As long as I'm not at the end, I should just check to make sure I'm going in this sequence. And if at any moment I break the sequence, then I set the result to be false. Okay, so let's check this. None of these should be the goal. So maybe I'll also just print real quick. Print n.isGoal. So false, false, false. Okay, that's promising. Let me make sure that the goal state is actually the goal. So if I make a state that has the goal in it, 1, 2, 3, 4, 5, 6, 7, 8, blank. So let me print goal.isGoal. That should be a true at the bottom there. Good. Okay, I think it's working. You know, I should test this more thoroughly, but in the interest of time, I'm going to keep going. Okay, so now what I'm going to do is grab the breadth first search code that I wrote on a previous module. So if you're rusty on breadth first search, you might want to go back and review this module. But for now, I'm going to take that code and I'm just going to copy and paste it and then see how I can edit it in this context. So let me go ahead and paste that into the solve method. And there's a few things I'm going to have to change. So first of all, okay, so I can keep using the frontier as a doubly linked list, because what I'm going to do is I'm always going to add, I'm actually always going to add things to the end of it. So So I'll say frontier.add last self. So I'm going to start off with this node on the frontier, this state, and I'm always going to remove from the beginning. So add to the end of the line, come out of the front of the line. That's what breadth first search does. So before I had the flexibility to support depth first search as well, but I'm just going to always do breadth first search now. Okay, now one thing that's going to have to change here though is we got to be a little bit careful how we keep track of what's been visited and what's on the frontier. So if I look at the way that everything's being generated here, let's imagine, I start off with this on the frontier. Then I expand these neighbors. Right? I take this off the frontier, it's been visited, so somehow I want to mark this as visited. And then I add these 3 neighbors to the frontier. And let's say that this one comes off next, right? And I'm going to expand its neighbors, one of which is this, the starting state. But that's already been visited. Problem is, when I generate this starting state from this neighbor, it's going to be a different object, but with the same data. So unlike before, where we had a graph that up front we just declared all the vertices, put them in a data structure, and we could refer to the same vertex each time as the same object. Here it's a little bit different. We may have a copy of an object that we've created and we want to check to see if it's been visited, but that's a copy of the object. If we were going to try to store .visited, or if we were going to try to store the state inside of the object, it wouldn't be the same. So what we need a way of doing is comparing and using a set, really, to keep track of what's on the frontier and what's been visited. So I'll make a set called onFrontier, and I'll start that off with this element. And I'll make a set called onVisited, or visited, which starts off as an empty set because I haven't visited anything yet. And so rather than saying keeping track of this in a state, let me instead add it to a set. And that set is only going to store one copy of each thing, and I can check to say, is it there or not? So I'll say here, okay, so when it's been visited, I'll say visited.addv. And at that point, it's coming off of the frontier, right? So I have this other data structure. In addition to the frontier, I have another data structure where I can quickly look up whether it's on the frontier or not. Because it might be on the frontier, but it's like somewhere in the middle. I would like to be able to efficiently check that. Before I did it by storing that variable state inside the object, but I can't do that for the reason that I explained here. So instead what I'll do is I'll say, okay, it's added to that set, it comes off the frontier. So I'll say .remove v. All right, if I print this, it might become a little bit unwieldy. Okay, so, but that's, so that's the major change we have to make here. The other thing we should do is, so we're gonna have to just basically update the code to deal with that. So rather than saying n.state is not equal to frontier, we should say if n not in on frontier. I know that looks weird, but if n is not in the set on frontier, that's how we quickly check to see if it's on the frontier or not. And n is not in visited. Then this is something that we can add to the frontier. And so doing that, instead of saying n.state is frontier, I would say on frontier .add n. And then we make sure to add it to the end of the queue as well. Okay. So that's looking all right. But actually, we got to be a little bit careful here because we don't have the functionality yet to really do this properly. Because we didn't even really know. So let me show you here. The main issue is that okay, let's say I make another state. I'll get rid of this now. Let's say I make another state. I'll call this state 1, I'll call this state 2. They have the exact same data. If I were to go print state 1 equals state 2, let's go run that. So if I do that, that is going to print false, okay? Because it's comparing, it doesn't know how to compare these objects. I never told it how to compare these objects. It's just comparing their memory addresses, and they're not the same because they're actually different objects. So one thing I have to do is actually go up and define another part of the Python data model, which is equality. So I'll define a thing here, so I'll say EQ, self other. And so I have a way of turning these into strings. So I'll just return, if they're the same, their string representation should be the same. So a very quick way to do this would be say return str self equals str other. So now when I run this, it'll be true. So that's good. So even if they're different objects but they have the same data, it'll be true. But there is another problem though. So if I'm using these set data structures to store the things that are on the frontier and the things that have been visited so that I can quickly look them up. Well, so let's see what happens when I do that down here. So let's pretend that I made a little set like this, and I said visited.add state1 and visited.add state2. And let's just print out what visited is. And it says unhashable type state. Okay, so we never told it how to give a hash code to this object, and so it's not able to put it into a set or a dictionary as a key or anything like that. So I also need to define a hash code, and I guess I can do the same thing I did for equality. I mean, there's a couple things I can do, but just to keep it simple, I'll just return hash of the string representation of this. I could also, just to show you, I could also return, well, first show that this actually works. Okay, good. So I added two of the same thing, but I have the equality method. It knows they're the same. It knows how to hash them, so I can actually use it. But just to show you, another thing I could do is I could return a hash code of the tuple of, let me use a tuple comprehension here. I'll say tuple, tuple x for x in self.tiles. This is going to convert the two-dimensional array into a two-dimensional tuple, and if it's a tuple, it can't be modified, so it's immutable, and so I can actually compute a hash code of it. That works too. But I don't know, which one do I like better? I'll keep this one. It's a little fancier. Whatever. Fancier is not always better, but this is actually a little bit more direct because it doesn't convert it to a string, so it's able to hash on the numbers. Okay. All right, cool. Great. So we should be able to use these now. So I'm getting close to the point where I can run this. But right now, what this will do is this will expand the entire graph, everything that's reachable from the starting state, and I might actually get to the goal way before that. So let me define a Boolean that says whether I'm finished or not, and if this thing I just took off the frontier is a goal, well then I'm finished. And I only need to keep going if I'm not finished. And so I'll add that here. I'll say while not finished, and length of frontier is greater than 0. So I can stop early if I've gotten to the goal. So let me just see if I'm able to get to the goal. So does this loop ever stop? And let me get rid of most of the print stuff. Maybe what I'll do is I'll print the size of the frontier, just to make sure it's not blowing up and going into infinite loop. So I'll print the length of the frontier. And let me also print, once this is done, let me print out v to make sure I actually reach the goal. That's not what I want to do. Okay, I need to actually call the solve method on the state. So let me go back and I only need one of them. Let me go ahead and say state.solve. And that's going to call this method. It's going to do the breadth first search. We're going to keep track of how big the frontier is. And then eventually we should finish this thing up. Okay, so let's try it. It says key error 567 blank for 7. Okay, so it's trying to remove something from being on the frontier, but apparently it's not there. So let's have a look at this and see if we can find the problem. Okay, so every time I'm putting something on the frontier, I say add it to that. So I'll keep tracking of it there. I start off with the frontier having this element. Okay, let me just take a look at this for 1 second, see if I can find the problem. All right, so I found the problem. For some reason, the hashing, this tuple comprehension didn't work as I expected. So what I'm going to do instead is say tuple list of this. So I'm going to do a list comprehension. I'm not sure what happened there, but yeah, so it wasn't actually, it was going to the wrong bucket in the hash table. Okay, so let me try to run this now. Okay, so we don't have the key error anymore, but we do have another error. It says state object has no attribute neighbors, and that's because we actually constructed neighbors on the fly. Unlike the graph before, they're not stored as, you know, a list of neighbors or dictionary neighbors. We've got to call this method here. So get neighbors. Okay. So I think I'm getting there. Let me just, print the length of the frontier. And then when I get to the end, actually, let me not print it out here. Let me get the scoping right. I'll just, if I've gotten to the goal, I'll say I'm finished, and I'll say goal, you know, and then I'll print out what that is. Okay, so let's try this now. Okay, so you see the frontier is getting bigger, but it's getting kind of big, but now it's decreasing a little bit, and it looks like we got to the goal. Nice. Okay, took a little while, but we got there. And you know, if you ever take artificial intelligence with me, I'll explain how to do this a better way using something called A-star search. But breadth first search will get us the answer. That's great. But how did I get that answer? What were the steps that I took to get there? It would be helpful if I could remember that. And so let me go back here and think about, well, how could I trace back my steps? And so you might, if you're really paying attention, you might notice I had one extra variable I defined as an instance variable here called prev. So I'm actually going to store a reference to the previous state that gave rise to this. And then that will allow me to back trace. So what I'll do is say, okay, when I'm about to put a neighbor on the frontier, I want to remember that this neighbor actually came from this state V. All right? So I'm going to remember, before I put it on the frontier, where did it just expand from? And then I'll try to trace it back. So what I can do now is say, all right, let me start with, you know, that goal vertex. And so now I'll say, okay, while v.prev, so I guess I'll say, okay, prev should start out being none. Okay, so while the previous is not none, I haven't traced back to the beginning yet. And so I'll just keep chasing back these arrows. It's exactly like we've done for other dynamic programming problems. We're just going to chase back these arrows until we get back to where we started. So I'll say, okay, v is equal to v.prev, and I'll go ahead and add that to the solution. And then, so this goes from the backwards, this goes from the end to the beginning, so let me just reverse this list. And yeah, I don't have to print all this stuff anymore. Maybe I will print the length of the frontier just to see I'm making progress. But yeah, let me now say solution is equal to state.solve, and let me go ahead and print everything in the solution. So I'll say for x in solution, print x, and then maybe print, or I'll say, you know, another line break there. Okay, so let's try to run this. All right, and see what happens. So I'm gonna run this again and see if it tells me, okay, it says list object has no, okay. I meant to say append. That's always frustrating. Okay, let's try it one more time. And supposedly this is the solution. So what I would like to do is go back to my page and see, can I, it's totally cheating, okay? But can I follow the plan here? So, okay, let's just see. I started with 5, 6, 8, blank 4, 7. So this is, okay, the first thing you should do is move the 1 up. Okay, the next thing you should do is move the 3 to the left. Next thing you should do is move the 4 down. Next thing you should do is move the 1 to the right. Now move the 3 up. Now move the 4 to the left. Now move the 2 to the left. Now move the 7 down. Now move the 8 down. Now move the 6 to the right. Now move the 1 up. Now move the 3 over. Now move the 5 down. Now move the 1 to the left. Now move the 3 up. Now move the 2 up. Now move the 7 to the left. Now move the, wait, I move the 7 to the left. Oh yeah, now move the 8 down. Now move the 6 down. Now move the 3 to the right. Now move the 2 up. Now move the 5 to the right. Now move the 4 up. Oh, I can see it. Haha. Now move the 7 to the left. Now move the 8 to the left. Oh, we got it. Look at that. Okay. So the key again to doing this, so once you've done breadth first search, just make sure, okay, as you're going along, you remember what the previous node was that put you on the frontier, and then just trace back until you get back to the beginning. And there you have it. So that's a simple way of solving breadth first search. Or it's a simple way of solving a puzzle using breadth first search. So I will include a link to the solution in the description. But I would encourage you, if you're a teacher and you're sharing this with your students, have them try it themselves first with the starter code that I have on the website. And you might also want to, after you watch this video, see if you can go replicate it yourself. So I'll also provide a link to the page with the starter code. Okay, so have fun though. This is a great way to represent state spaces and solve problems. It's an example of classical search in artificial intelligence.